Yeah. Okay. So welcome everybody to the DTP colloquium. Today, a great pleasure to have our very own Gautam Mandal. Of course, Gautam needs no introduction, so I won't introduce it. But it's a real great pleasure to have him here. And he's going to tell us about phase-space hydrodynamics methods for loading. So Gautam, please.
Thank you, Omkar. So I should thank Omkar and Vivek for interesting me to give this colloquium. The genesis of this is the last week's colloquium, in which some elements of hydrodynamics of relative systems were talked about. And so I thought that, I should describe some method which we call phase-space hydrodynamics method. The main thing here is, of course, I will describe some results and applications of this method, but the tools themselves are also important. And, please ask me, after the colloquium, because I'm not sure how much I'll be, but it's a rather nice first principle method of deriving some hydrodynamic description of fermionic systems or hardcore systems in 1 and 2 dimensions. Mainly 1 plus 1 dimension, but I'll also describe some 2 dimensions. So these are the various. Is this some stick or something? I'll try. Oh, I can use this.
Okay, I'll try to get your point right.
Okay, thank you. So let me get started. So let me first give you the general context of in which this particular problem that I'm going to talk about sits. So this is about long-time dynamics of non-equilibrium states. So there's a rich set of questions about long-time dynamics that you can ask. So the first question is somewhat qualitative. It's about whether a given system equilibrates. And if it does, then what are the variables that I'm looking at which show equilibration? And with what's the initial state that I start with? And so then we ask more. Yeah, thank you. Then we ask more quantitative questions. That's about the nature of the equilibrium. So if it does equilibrate, does it equilibrate to a thermal ensemble? Or in case of integrable systems, does it equilibrate to a generalized Gibbs ensemble, which has temperature as well as an infinite number of chemical potentials? Or does it retain some memory initial state? And in case of this whole class of Kibble-Zubek methods of long time dynamics in which you are introducing a flow quench and so on, or dynamical phase solutions and so on and so forth, effect density generation. Anyway, there's a lot of stuff that you can ask about this, and then more quantitative questions about rate of approach to equilibrium. So, for example, whether there is exponential, power law, what exponents, and so forth. And then there's a more general class of questions, which is like, as in equilibrium physics, you have universality classes and critical exponents for critical phenomena, whether there are universality classes of asymptotic state in case of non-equilibrium phenomena, and of some universal relaxation rates. So these are some general questions. So how does one study these questions? One favorite method of experimentally studying a theorist is the so-called quantum quench. To start with the Hamiltonian, and you have some coupling constant like the transverse magnetic field in case of this Eisenhower example, or just a scalar field theory in which there's this mass. And so these are made time dependent, and you make a sudden change which is called a sudden quench, or a slow change, which is called a slow quench. And you start with some system here, maybe the ground state of the original system. And so after this time development, you arrive here at some non-equilibrium state, and you get the further development of the system under the new Hamiltonian. Okay, so this is called a quantum quench. So what are the theoretical methods that are available? So primary method is numerical. So you do this time development numerically and see what you can get. There are analytical methods. So I'll give examples. So this will not be an exhaustive review of this area. There are many different kinds of work. So I'll give some examples of which I am familiar with. So there are situations in which analytical methods are available. For example, when the post-quench system is gapless, the conformal theory, particularly in 1 plus 1 dimensional, there are powerful techniques of dealing with conformal field theories. Or in higher dimensions, we have been able to derive some results with free theories, bosonic or fermionic, or large n when models which are effectively free for the questions that we ask. Okay, so one can show that in these systems provided under sort of reasonably broad class of assumptions, the system equilibrious, thermal or GG state. And its properties as well as relaxation rates are dictated by universal conformal field theory properties, like the spectrum of anomalous dimensions and so on, and the central charge. So that's the universality that I talked about.
So in the previous slide, you gave this example of message here, change the mass. After quenching, there's that.
So if the mass was 0 after the quenching, then it will correspond to a conformal field theory. So of course, that's a conformal field. In 1 plus 1 dimension, you can do better. Not just a massless free scalar field, but you can talk about conformal field theories in general and show some of these results. So in case of the free theories in the higher dimensions, general dimensions, you can show some interesting things about free field theories. These are also true about when models that depending on whether the space-time dimension is the spatial dimension is odd or even, the approach to equilibrium is exponential or power. So these are things which. So this is a very quick review of what's been done, particularly the kinds of work that I have been involved with, and of course you can also apply holography. So so in the context of ADS-CFT, a black hole is described by a dual quantum system in equilibrium. Okay, so as a result, the black hole formation can be related to thermalization and in particular relaxation rates of approach to a thermal equilibrium can be related to quasi-normal decay rates of black holes. So you can derive results about relaxation rates of approach to these generalized gifts ensemble as well using gravity methods. And there are also this this recent, very simple example of holography, where you can show that the heat loss to a bath can be related to Hawking radiation. So that's the general context.
So,
yeah.
Point number 2, I think. Sorry, maybe point number 1. The universality.
Yes.
That was true in 1 plus 1 dimension. Or in the pre-higher dimension, is this gamma that you had, is that governed by some anomalous dimension or something else?
So here, this was for free field series, so it was just given by dimension.
Just given by the dimension.
Yeah. Right.
But is it like I'm thinking of this gamma as sort of quasi-normal mode frequency of the lightest quasi-normal mode thing. In 1 plus 1 dimensions, that's determined by the spectrum.
So good. So in 1 plus 1 dimension, this gamma has a lot of rich physics. So that's given by in a conformal field theory, it's given by the lowest anomalous dimension available. in the spectrum.
But there's no analogous understanding in higher frequency.
No, this is just given by the dimension of the because even in the well model, you don't do much more than frequency. Yeah, right. But the this d equal to odd, of course, includes d equal to 1. There, this gamma has a lot. In particular, yeah. So
and sorry, this difference between odd and even, is this connected to the difference between propagators being on the delta function and power?
Which you know very well, of course, you have used it. Yeah. We tried to make that connection more, but besides, sort of observing some mathematical similarities, we couldn't quite do this. But yeah, right. So Shiraz can explain what he meant, or I can explain later on. So anyway, so the something.
Sorry, Gautam. Can I ask a question? To your point number 1, what kind of physical systems is this, will go to a CFT or a free or large in theory post quench? Like, for what systems is this a good?
So yeah. So the so for example, you can take take any example of a critical point. Let's say a second order phase transition point of a system, okay? And then let us say you start from your value of the coupling, which is not critical. Okay? You start from something else, and then you quench it to the critical value. Okay, so that will be conformal. The post quench system then will be a critical system, conformal system. Okay.
Okay.
But just in very simple terms, if you're doing a quench which is spatially translationally invariant, then intuitively I was thinking you dump uniformly energy everywhere in the system. So I mean, if you basically thermalize, and so are there two kinds of things? Let's say you're doing a little faster quench. First, deposit the energy, and then that energy has to be spread out through conduction of heat, etc., and then it is it like that? Or so the basic picture.
The point is that you dump some energy into the system. Yeah. Okay. So let's say you talk about the sudden quench. You dump some energy into the system. So it's a high energy state that you have created. Okay. Let's say even the ground state of the old Hamiltonian is a high energy state, but typically it's not an eigenstate of the new Hamiltonian. So that's the thing. That's what gives time dependence. So even in the case of the slow quench, relatively slow quench, you have given it enough time to these transients that you talked about. Okay. Let's say I have given enough time for those transients to dry out. But now I have a system of the new Hamiltonian, okay, which is time independent from henceforth. Okay. But it's some state which has energy, it's an excited state, and it's a non-stationary state, typically. So that's.
You create the black brain, and then there are excitations that settle down on that. Maybe those are the two processes.
Yeah, because that process is heat conduction, no? All your hydrodynamic modes will dissipate.
But there are no hydrodynamic modes turned on because of transition.
It's just if I saw the energy and translation in very way, it's very
maybe the one that you were thinking of is
just excite the system in some way.
In philosophy, it's a very good concept. I mean, it just makes the brain, but the brain is not really made in equilibrium. That's some settling down process.
So you can think of something simpler, in which you start with an equilibrium, perturb it a little bit, and then see, the various rates of going back to the equilibrium. So that would be perhaps even more closer to the this
Gautam, in many condensed matter examples, the way we think about it is that it has the energy content which would correspond to equilibrium at the critical point. But the way energy is distributed between different modes is all wrong. And there's got to be a lot of redistribution of energy to settle down into the critical state, and that's what it is that you're studying. Is that
Absolutely correct. Absolutely correct. So the total energy indeed is going to remain, because it's a conservative system, is going to remain, and in fact, the total energy and the total other charges, they are going to describe the various chemical potentials of the final equilibrium state. But it's a redistribution, the local redistribution of the energy. And so, in fact, I'm going to give some examples of this phenomena. How really, even with all the conservation, how equilibrium happening. So there are some beautiful graphs that hopefully I'll have time to go to. Okay, so anyway, that's the general context. In this talk, I'm going to talk about some particular problem of how to develop sort of post-quench time evolution of a Fermi gas, one-dimensional, 1 plus 1-dimensional Fermi gas, or a hardcore Bose gas, which would be equivalent for my purposes here. So in the limit of infinite hardcore repulsion, this is called the Tonks limit, is called the Tonks gas, and in 1 plus 1 dimension, as well as in a sort of limited way in 2 plus 1 dimensions. So hopefully I'll get time to go to that. These problems have some experimental significance in cold vacuum systems also. So some really lovely experiments have been done by this group of Kinoshita and DeMarco and so on. Okay. So the method that I'm going to describe here is, it arose in early applications of the context of C equal to 1 matrix model, which came from string theory. And it also, this method also arose in the context of giant gravitons and Subayama's theory in low dimensions and so on. Okay, so so just one slide of string theory, how this Fermi gas comes from string theory. So string propagation is described in terms of fluctuating Riemann surfaces in which there are metric degrees of freedom on the world sheet. So the summation of a matrix is given by a summation of a matrix model Feynman diagrams. Don't ask me how. So the matrix model Feynman diagrams, correspond to some triangulated Riemann surface, and sum over various triangulations is given by the partition function sum over various Feynman diagrams, and in the limit of very dense triangulations, which is the limit typically of large n matrix models, as well as some critical scaling that you have to do. So there's some stuff for double scaling. Anyway, never mind. So the matrix model, when it is a one-dimensional matrix model, that corresponds to matrix quantum mechanics matrix as a function of n by n matrix as a function of time. And when you change variables from the matrices to the eigenvalues, so there's a Jacobian that you pick up. That's a completely antisymmetric function of these eigenvalues. So because it's completely antisymmetric, the wave functions written in terms of eigenvalues becomes fermionic, and this interaction piece here, what appeared like interactions in case of the matrices, that becomes like an external potential phase by this fermions. Okay, so this is just for I'm sure that this was not enough. I didn't give it enough time to explain, but so here's the plan for the rest of the talk. So I give you the general context. I'll explain what the problem is. The problem will be that of shock formation in this Fermi fluid or the Bose fluid. Okay, that will be the problem. And so first, I'll have to spend a little bit of time. These are the tools that I'm talking about. These are some beautiful stuff about use of coherent phase to describe the droplet picture of phase-space hydrodynamics. And so that will be the derivation. And using this phase-space hydrodynamics, my first result will be to cure the deficiencies of conventional hydrodynamics, which cannot, fail at the time when the shock fronts develop, and you cannot go any further. Okay, so that will be that.
Are we in the translation in the equation? Or you're not? Now, the shocks that come from phase?
It's not a constitution.
Not.
Yeah, I mean, your potential can be, so I'll describe situations in which the post-coin system, okay, is free. Okay, the Hamiltonian will be just P square. There is no external potential, but your initial fluid profile.
So the quench was not translational then?
The quench is not translational, right? So, correct.
So now in this case, what Sandeep said would happen, right? That the hydrodynamics at play at least right?
Yeah. So, yeah. Yeah.
So just to understand, this part of the talk is basically hydrodynamics or is it the hydrodynamics itself will break down because of the profile?
The normal hydrodynamics in terms of real space densities will break down. But the hydrodynamics in terms of phase space densities will not break down. Okay? Just to let the cat out of the bag, basically, when the shock forms in terms of real space hydrodynamics, real space density, so there's an infinite derivative that happens. Del rho del x becomes infinity at a particular time. Okay, but in terms of phase space, these are just folds. Folds become shocks. So folds are smooth objects. Okay, in terms of phase space description. Okay, so that's what basically. Okay, and then once you are able to go past the formation of the shock fronts, of course you can ask about T going to infinity questions. Okay, and what we find is that indeed in this case also it equilibrates and it gives equilibrates to a generalized Gibson sum because it's a free Fermi gas, so therefore it has infinite number of conserved charges, and it does. And I'll explain what those charges are. And then you can also describe, therefore, the universal relaxation exponent from the shape of the confining potential. So you start with some shape of, so there's a universality class of the shapes of the confining potential, which you, one example is that you have a trap. So Fermi fluid in a trap, and you just switch off the trap. Okay, like some optical lattice, just switch it off. From the shape of the trap, okay, the initial Fermi fluid, the initial configuration of the Fermi fluid is given by the shape of the confining trap, and so there's a certain classification that you can give of the shapes, and depending on the class of shape, the exponent is a power law relaxation. And the exponent of the power law is given by the class of shapes. Okay, and then 2 plus 1 dimension, that's the ongoing work. That's about fermions in a rotating, two-dimensional fermions in a rotating trap. And so it has rotation as well as it has a confining potential. So this actually maps to very beautifully the Landau problem. Okay. And in case of the lowest Landau level of those fermions, you can apply our methods back again because secretly the lowest Landau level makes the 2 dimensions as a phase space. So the initial 4-dimensional phase space becomes a 2-dimensional phase space. So our methods start working again.
Can we ask about the phase transition of the function?
There's no phase transition. There's nothing that happens afterwards. So I'll come to it. Yeah. So let me, so I've said that a lot of these things anyway, perhaps. So suppose you have a system of non-interacting fermions of the Storm gas, which are suddenly released by confining potential to free space or to a different confining potential. So for example, a different value of the shape parameter. Okay, so let's say from the potential being kx squared to k prime x squared. These are examples. Quench. Such systems have been realized in, okay, I have mentioned these experiments. I mean, I do advise to all the theorists here to read these experimental papers. They're absolutely fabulous. So anyway, the thing is that, so for many purposes, in particular for quantities of interest rate, the Bose system in the Tonks limit can be treated identically in the Fermi gas. So therefore, from here on, I'll use the language of fermions.
What do you mean by the non-interacting fermion proportion is infinite? Because you said non-interacting.
No, sorry. The non-interacting fermions, comma, or bosons with infinite. Right.
These are non-relativistic.
Non-relativistic. Yeah. Okay. So note that even for non-interactive systems, the post-quench evolution can have rich physics, which will come to all that. The exact treatment requires, so you can do an exact treatment of this system, of course. Okay. Namely, that you have to find out the single particle eigenstates before and after the quench. The old and new oscillators, they get related by Bogoliubov transformation, compute that Bogoliubov transformation, and then express the old Fermi C. If you started in the ground state, express the old Fermi C in terms of many-body eigenstates of the new Hamiltonian. Okay, you can do this. This can all be done, but by the time you have reached the number of particles equal to 20, 30, 40, and so on and so forth, okay, your mathematical program starts crashing. Okay, so it's very difficult. Okay. Now, conventional. So, what do you do then? Okay, is there some sort of analytic treatment that you can try? So, when the number of particles is large, it's natural to try continuum description in terms of the density. This is the real phase density that we're talking about. The fermion density and the velocity of these particles. The evolution of the particle density is assumed to satisfy and the velocity satisfy the continuity in Euler equation. So this just comes from number continuity, okay, as this is the standard continuity equation, and this comes from the sort of Newton's law, okay, the momentum conservation, the amount of by which momentum changes because of external force. So this term is about external force. This is a potential. This is an external potential in which the fermions are put, and this term comes from the Fermi degeneracy force pressure. Okay, namely that there is a there are papers which have derived this equation in a sort of Gross-Pitaevsky mean field approximation, in which the rho times v is this term is the usual external potential energy due to the external thing, and this is the energy of the Fermi C, and you replace this rho cube by a mean field rho square times rho. Okay, with that you get this equation. But anyway, I'm going to derive this equation from first principles, okay, in an approximation, and then I'll show that that's really an approximation, and if you don't do that approximation, then you can go ahead with. Okay, so let me say what the so you see that here derivatives of the density start appearing. So therefore, at any time when del rho del x, okay, blows up, these equations do not work. Okay. So that's what I've said here. So now attempts have been made to deal with this problem by adding extra terms to the Euler equation. For example, the so-called quantum pressure term. So this is a term which has been added by these gentlemen, including my collaborator Manas. So the idea here is that you have done some mean field approximation here in deriving this equation. So therefore, you try to do some higher order correction and so on and so forth. So and however, the point is that adding these terms do not solve the problem. Okay, the problem is elsewhere. The time development beyond the shock cannot be computed, and let me show you some things. So here, this T less is the time. So I'm showing here the fluid profile. So that at T less, the fluid profile is like this. Okay, this M-shaped region. It's all nice. At T equal to T0, it starts becoming vertical. Okay, so del rho del x becomes infinite. And with this additional term that has been added, okay, if you apply the solution of the equation, it shows some high oscillations. So it shows irregular behavior beyond the top, and the numerical evolution is the dotted line, and you can see that the equation, the solution of the differential equation with the extra term does not agree with the numerical solution.
This might be very stupid. Instead of differential, can't we turn the equation into integral? Like when electrodynamics they discontinue the electric field outside and inside the field. So if we do numerical simulation using
so yeah, so in case of the shocks, people do try such things to say that there is some boundary condition. Put some boundary conditions before and after the shock and so on and so forth. You can try doing that, but actually none of this is needed. Okay? Because the singularity that appears here is actually only an apparent singularity because of the choice of coordinates on the face. Okay, that's what I'm doing. All right. So, so we'll solve this problem by using a large description of many fermion systems, which was introduced in the context of 3.1. So conventional hydrodynamics appears as an approximation from this. Phase-space hydrodynamics remains valid at all time and therefore can address. So I have already said hydrodynamics in the fermion phase space. Let's now start with the main part of the talk. So, so I have n fermions. Remember that I'm talking about n fermionic particles, free fermions, all in some external potential V of x. Okay, so the single particle Hamiltonian is this. There's a second quantized description which is easy to derive, namely by introducing a fermion, second quantized fermion field, which has the following mode expansion in terms of eigenfunctions of this single particle Hamiltonian. Okay. And so this, you can show that, from the fact that these are eigenfunctions, not from this fact, but the second quantized fermion satisfies this Dirac-like equation, non-relativistic, and this is, and it satisfies this constraint which says that there are n number of particles. So these are all very easy to show. This comes from the fact that the single particle, the single particle wave function satisfy the corresponding Schrodinger equation. Okay, all right. Okay, so this part is easy. Okay, let's now. So this is a rather busy slide. So we first say the contents of this. So I'm going to define a second quantized Wigner phase-space distribution. I'm going to explain all of this thing in the next few slides. Okay, so this is an example. This is an extension of the single particle Wigner phase-space distribution. I'll say what that is as well. Okay, two second quantized. So if these were just single wave functions, this size, then this would have been a single particle Wigner phase-space distribution. Now this psi is a second quantized field. Okay, so this is the second quantized Wigner phase-space distribution. The job of this is to describe the phase-space density of n number of particles at one shot. Okay, so that's what it does. Okay, now it's a very important idea that we're going to introduce here. I mean, it's not our idea. This is the idea of coherent states. So there is a certain algebra in a single particle, dynamics. It's called the W infinity algebra, related to just the Heisenberg algebra actually. So I'm going to explain all of this stuff. Okay. And you can describe the states of the system, okay, in terms of this coherent states of W infinity algebra, and the expectation values of this second quantized U xpt field, this Wigner phase-space distribution operator, in this coherent state, which I'll call the little u xpt, they satisfy some equation which is a very reasonable looking equation, except that you might have expected Poisson bracket here. Instead of Poisson bracket, it's a Moyal bracket. It's what is called a Moyal bracket, which is an h-bar deformation of the Poisson bracket. Okay. Now, I call it an h-bar deformation, but actually this is an exact result. Okay, I don't need to think of h-bar equal to 0 limit. This is actually an exact result which you can derive. Okay, and this expectation value u, it satisfies also some constraints. One comes from the fact that this, the total phase space, even the quantum phase space distribution, the integral of that should be equal to n. It just follows from this equation. That is easy to show. I'll derive all this. Even these are derived, and it satisfies the star product constraint. Okay, that also I'm going to derive very soon. So yeah.
Is there an element like say very high temperature compared to chemical of gas, where it is approximately plus, literally in the sense of additional terms in my brackets. I'm just asking you, because a very degenerate, you might think a very degenerate from the gas, but is there some opposite there?
So it's always true that in the large n limit, it becomes classical. That statement I can make, and in fact, that statement I can derive. Okay.
Sorry.
Yeah.
In this sense, increasing the density.
So I take the large n limit by taking n going to infinity and h bar going to 0, so that n h bar equal to remains 1. Okay, so that your phase space density becomes something of order 1, remains of order 1 quantity. So that the total integral of the phase space density becomes 1 in my units. Okay, so here I can say this already here. See, you can take the h bar on this other side and take the n going to infinity limit and h bar going to 0 limit, so that nh bar is equal to 1. So indeed, the phase space density is satisfies the property that you say. Okay, good. So now, yeah.
Gautam, this n is the total number of fermions, right?
Yes. Yes.
And I mean, you have these different classes of external potentials they can be in.
Yeah.
There should also be some scaling of the frequency associated with the potential when n goes to infinity. Otherwise, you will get infinite, to define the thermodynamics. Like we say, n goes to infinity, volume goes to infinity, ratio remains fixed, like that. Instead of volume, you have to have some length scale of the potential in place of the size of the box. So there's got to be something happening.
You're right about that. So the in the cases that we have looked at, if it's let's say particles in a box, okay, then n by L also remains fixed. And in case of the harmonic trap, a square root of omega plays the role of 1 upon L or something like that. So that's also correct. Yeah. So I have to.
And for different shapes of potential, there'll be like a different parameter that comes, like this square root omega will be replaced by something else.
That is correct.
Okay.
That is correct. So actually, it all follows. Yeah, that's correct. Okay, good. So yeah.
In Goldstein, there's an equation like that for single particle probability distribution, except that the right hand side is Poisson.
Yeah.
So the difference with the fact that it's not Poisson bracket but Moyal is because of the exclusion. Because you can't put two guys on top of each other.
The difference is because of the actually single particle quantum effects. It's actually at the level of the.
But the fact that you're doing many particles is not important. Just a single fermion will remain the same. If there's some uncertainty.
The single particle will also obey this equation. It's really h bar. It's not the uncertainty principle is this one. This guy. Okay. This in the h bar going to 0 limit will become the exclusion principle. Exclusion principle is this guy. So in the h bar going to 0 limit, the star product will become ordinary product. So it will be u square equal to u. So u can be either 0 or 1. So that will say that in a particular phase space point, there can be only one fermion or 0. Okay. So that's what I said.
So that is a related question. So in the standard kinetic theory, when you write down this single particle phase space density evolution, there is this hierarchy, right? The PGKY hierarchy.
Yeah.
So that closes only when the particles are non-interactive. So here,
that is right. That's a very good point. But you can also deal with. So I don't have time to get into that. But you can do some mean field theory with an interacting problem. Okay. and try to get that. But then your non-closure of this equation will comes into play, which, however, you can make a closed set of equations again by using this self-consistent ansatz and so on. Yeah, but otherwise you're right. So it's not a sort of closed system of equation. Okay, so there are 6. Okay, so this is a very important slide. It requires 6 ingredients. I don't know how many. So let me go. Single particle wave functions. Okay, and their Wigner phase-space distribution. So the typical example that people always give is, okay, so this is the definition of a Wigner phase-space distribution. This is the construct that was introduced by Wigner to describe a phase-space density or phase-space trajectory of particles. Okay, so that's given by this thing. So if you start with a wave packet state, which has a certain mean momentum and certain mean position, then you can see that the phase-space density is actually some peaked thing at x0 peak. Okay, so that's what this fellow is. Now, for let's do this. Let's apply this. Let's try to understand this thing in the case when the external potential is a simple harmonic oscillator potential, namely half x squared. The eigenfunctions are given by harmonic functions times the Gaussian, and the corresponding Wigner distributions are given by Laguerre polynomials multiplied by Gaussians, where these are functions of x squared plus p squared. Okay, so the radius, if you define polar coordinates in the phase space, okay, then it's independent of theta. It is dependent only on r. So as a result, you can plot things. You can plot this guy, okay, in a 1D plot, where this is the radius, radial variable. So x squared plus p squared is r squared. I should have written that here. So this is how it looks like. It stops at some point, depending on what is the order of the. So I have now plotted the Wigner phase-space distribution corresponding to the 50th, 50th eigen function in a 100 particle problem. Okay, and I have already done some scaling of h equal to 1 over n, but you don't have to do that as anyway. So this is how it looks like. The Wigner phase-space distribution is not much of a phase-space density, as you can see, because it becomes negative. Okay, as Onkar pointed out with this plot yesterday, that apparently these days there is some understanding that very quantum states can have negative phase-space Wigner phase-space distribution thing. However, once I go to the next slide,
this asks the phase-space.
Yes, x squared plus b squared, square root of x squared plus b squared. Now, it's easy to show. So this is an important slide. It's easy to show that the second quantized, the ground state expectation value, the ground state is the field formation, I'll call that f0, and other states I'll call f. So anyway, so the expectation value of the second quantized Wigner phase-space distribution is the sum of single particle Wigner phase-space distributions of the occupied levels. Okay, how does one prove that? That's easy actually. So the remember that the second quantized guy is Wigner phase-space distribution given by that. It has this mode expansion, and the Fermi C is built like this, and it's easy to show that Bn dagger Bm, okay, is 0 if it is m is greater than n, and is 1 if it is less than n. Okay, so that's what it is. As a result, out of this whole stuff, it becomes like single particle Wigner phase-space distributions of the occupied levels. That's all. Okay. Now I have simply plotted it for n equal to 100. Okay. As you can see, it starts approaching the n equal to infinity. I'll explain to you how this n equal to infinity limit can be derived. Okay, independently. So it reaches there. Okay. And now this guy is nowhere near negative. Okay, it's well clear of anything negative. Okay, so eventually in the n equal to 1 infinity limit, u just becomes 1. Okay, 1 or 0. Okay, that's what it becomes. So here it is. So these are all 1D plots. Okay, but actually uxp is a function of 2 variables. So here's a contour plot like this. So ignore all these deformities here. Actually, these are circularly symmetric plots. This is what happens for n equal to 30, and this is what happens for n equal to infinity. You can actually derive the size of this blob from the normalization condition of this one. Okay. So first of all, you can show that it becomes a uniform blob. Okay, with u equal to 1 region and u equal to 0 to the region separated out, and u equal to 1 regions, the size of that you can figure out. Okay, let me show you how. Okay, so that's ingredient number 3. So I wish this was a class rather than a lecture. All right. So I need the notion of while ordered operators. So given any phase space function, like xp squared. Okay. xp square, what is the operator corresponding there? Is it x hat p hat square, or is it like p hat x hat p hat, or what? Okay, so there is a notion of while ordering of operators. That so how do you get at that? So there are these. There's a nice basis of operators in a single particle Hilbert space given by this. Okay, this is called g hat xp, g tilde xp is given by this construction. Never mind, this is all two. And they satisfy some multiplication algebra and the commutation algebra, in which things like the star product and the Moyle bracket starts appearing already, as you can see. So Shiraz, here it is. So this is single particle quantum mechanics actually, and these structures do appear here. Okay, so now if you have a single particle operator O, then okay, so this is how this while ordering works. Suppose you have a function OXP, okay, and then you multiply this by G tilde XP and sum over all possible XPs. So this particular linear combination becomes a while ordered operator. Okay, so these are very important ingredients. So by the way, the multiplication algebra and the commutation algebra together, whichever you want to look at, it's called the W infinity. This okay, and the point is that using this basis of W infinity generators, you can go from phase space functions to operators, in particular to while ordered operators. Now, I'll just give you without the proofs are all here in the slide, but let me just tell you the results. The operator product becomes star product in this basis. Okay, and operator commutation relations becomes Moyle bracket in this basis. Okay, so that's what thing is. From here, you can actually get something important, which is so first of all, I missed this one. So if you start from an operator, which is the projection operator, the pure state density operator, like this, then the corresponding phase space function is the Wigner phase space. So projection operators for a particular state psi go to the Wigner phase space distribution of that thing. So the phase space function is the Wigner phase space distribution. So that's the this together with the fact that rho psi square equal to rho psi, because the projection operator tells you that the star product of the Wigner phase space distribution of psi with itself must be, so u psi star u psi is equal to u psi. Okay, and also if psi and phi are orthogonal, then you can show that the star product is equal to 0. Because when you are doing star product in the phase space, you are basically doing operator product in the Hilbert space. Okay, so that's the thing. Using these two, you can easily do. Oh, also the trace of an operator is just an integral, okay, of the phase space function. That also is easy to show. Okay, now I can prove this thing for at least for the ground state expectation values. I can prove that U naught star U naught is equal to U naught. Okay, how does that work? So U naught, remember, we have already proved that it is the sum over these single particle distributions for the occupied states. And now this star product becomes this way. So using the orthogonality as well as the unit u star u equal to u as well as the orthogonality, I have this. Okay. So m and n, if they're different, they don't click. Otherwise, it just becomes itself. So there you are. Okay. And the integral of u naught, okay, is actually I forgot to say that because of the trace, because of the identification of the trace to the integral, the integral over the phase space becomes trace, and as a result, for the projection operator, it just becomes 1. Okay. So now the integral of u naught, which is a sum over n such things, becomes n. Okay, so that's the proof. Okay. So, and now when I want to take this large n element, you see, this is going to become u naught square equal to u naught, and I'll take the h bar there, and integral of u naught will become 1. Okay, but I have only done the ground state here. I have to describe the other states. Okay.
Yeah, I'm understanding you're saying for the ground state, the operator was the sum of n orthogonal projectors on orthogonal one-dimensional subspaces, and then that squares to itself.
Right.
Therefore, it's diagonal.
Exactly. Exactly right. Okay. Now let me go to other states. How to form other non-trivial states of the fermion theory, okay, and not just the ground state. Okay, so this is here. I have to use this W infinity coherent state construction in the second quantum theory. Okay, so I start with the result for the sandwich homomorphism. Okay, I call it the sandwich homomorphism, which is the following. So if you have this integral psi dagger x, some operator here, O1 psi, and commute that with psi dagger O2 psi, then it's psi dagger O1 O2 commutative to psi. This is something that we use all the time in quantum field theory, in constructing Lorentz generators in a fermionic field theory. Okay, take these as the Lorentz generator, kinematic Lorentz generators, sandwich them within this one, so the commutation of sandwiches becomes like the commutation of meats. Pardon. So this gives a representation of single particle operator in the algebra, named specifically the W infinity algebra in the second quantized fermion theory. Okay. Now I can now do the following operation. So let's say that I have consider a unitary operator in the single particle theory, e to the power IA. So that's the W infinity group element.
What was the W infinity algebra?
So it was just the it is just the algebra of these exponential operators. These guys.
So in that x is a number.
X is capital X. Capital S it should be hatted. It's an operator, and little x is a number, and capital P is hatted, is an operator, and little p is a number.
So I should think of this as roughly delta function where x is equal to operator x is little x and operator p is little p, except that they don't commute just one. If these were numbers, this would be setting.
If these were numbers, they would be like that's it. But this while ordering comes precisely because of they not being numbers. And the other terms in the ordering, they come because they are not numbers.
So this is like, is this like the Moyal? Is it like the operator corresponding to the delta function? You told us given a function in phase space, you can make an operator. Now, if I take the function that's delta function at x and p, is this that operator?
Presuming.
Okay.
Presuming.
Sorry, I just asked.
Yeah.
You said that the Moyal bracket comes first of bracket. If I understood.
Yes.
When n goes to infinity, h bar goes to infinity.
Yes. Yeah, in case of single particle, I'll just take h bar going to 0 because there is no n. So then it becomes small bracket becomes possible.
So even with n particles, this limit always landing on the class sits in a kind of class.
Yeah. So I'll come to that very quickly. Now the thing is that yeah.
So in that case, the regional density that within our gives positive, you have the usual class.
Yeah. Not only that, in the large n limit, n going to infinity, h bar going to 0, that kind of limit, in fact u will become 1 or 0. Okay. There's no question of negativity.
Classically, when you take the product of two delta functions, you would get 0 unless the two delta functions were at equal points, and then you get something missing.
Yeah.
Here, presumably, you take the product of these two delta functions and you get something that's very. Meaning, if you now wrote it in terms of these, I'm asking, what is the product of two of these guys?
Oh, what's the product of those two guys? Yeah, here it is. So that's it. So yeah, good. So there's an finite h bar spreading out of this product of delta function.
I thought it would become infinitely spread. That's wrong.
Not infinitely. No, not really. Okay. I mean, this is what. Okay. Yeah. It's just in the h bar going to 0 limit. It's just one set of derivatives. I mean, at first order, but it's actually finite. For finite h bar, it's actually finite spread.
Yeah. So there is a clear question. There's an answer to the question: delta of x1 p1 star delta of x2 p2. What is that equal to? What is the Moyal star of delta of x1 p1 delta of x2? I should know this. I thought that was infinitely spread.
That should, whatever comes from here.
So you have
I have not done it. All right, good. Let's go. So now the point is that yeah. So anyway, you can on single particle Hilbert space states, you can apply this this group element e to the power I little a, where little a is some linear combination of these W infinity generators, and the corresponding thing that you do in the second quantized theory is just capital A, where capital A is just this. Okay, this happens because of the sandwich homomorphism that I talked about. So now, without further details of this thing, let me say that you can prove this, that if you take this F to be a W infinity coherent state starting from this ground state, the Fermi sea. Okay, this is how you construct coherent states. You take a group representative and act on some lowest weight state in some particular representation, and you construct this one. So here, the equivalent of the lowest weight state I have taken to be the Fermi sea. Okay, so you get this stuff. Anyway, this is a lot of details here, which I'm not sure I'm explaining very well.
Just the one, what is this W infinity group? You explain that one element.
W infinity group is just given by the so this is the W infinity. This is the W infinity algebra.
Algebra that commutator is Moyal commutator.
Commutator is the Moyal commutator. More or less the Moyal commutator, but you actually have G tilde XP with the deltas inside. So the Moyal stuff comes when you take two operators. So this is where the Moyal stuff comes. When you take the integrals with O1 XP and O2 X prime P prime and do your partial integrations, then you get this. This is the Moyal.
But if I instead of operator, I think of the function corresponding to the operator, then that would just be Moyal commutator.
Yeah. Here it is. So you are looking for what if I use deltas there? Yeah. Maybe that's an interesting question. Yeah.
But the idea of the Moyal, I'm thinking it's functions of phase space and Moyal commutation of functions.
Yes, absolutely correct. That the Moyal commutation of phase space function is the algebra. Okay, good. So now it's perhaps not too difficult to digest that if I take this expectation value of the second quantized Wigner distribution thing, it becomes like a sum over Wigner distributions of n sum over n Wigner distributions. Each of this is the Wigner distribution for the state which has been rotated in the single particle state by this amount. Okay, so this is what it is. So as a result, it's like it's a new Fermi sea in which all the occupied eigenstates have been rotated by a single single particle rotation. Okay, so as a result, it's not.
I'm very sorry to interrupt, but just tell me, please, in this language, what is the W group? That is, how does it act on functions in phase space?
Yeah, so it is, you have to really, one way to think of this is the expanded and,
Is it similarity transformation with Moyal? Is firstly the W infinity group element, is it some function of phase space? Can I think of it as a function in phase space? And
yeah, so here it is. You can think of the expectation values. This you could do even in the single particle theory. So this will be exponential of the commutator.
But is an arbitrary function of phase space, arbitrary invertible function in phase space a W infinity group element? And does it act on other functions in phase space by similarity? That W star function star W inverse. Is that?
Yeah. Right. So that's what I'm doing here in the second quantized thing. But each of these statements is also true about the single particle state. So as a result, you get some stuff in which each fermion state. So it's like all the occupied states have been rotated in a single particle thing. As a result, this statement is true. U star U is equal to U again, and U is equal to integral of U is equal to N. Exactly like you did for the U naught, because now it's again a sum over N single particle distributions over sort of orthonormal states. Okay, so I have proved therefore this. Okay, I mean I have not given much time to this, but this is indeed the proof. And then you can, so Shiraz, maybe this is this is some of the things that you want. But infinitesimal transformation also you can prove by, let me not go into this one. So single infinitesimal transformation by W infinity algebra elements, which is just it becomes like Poisson bracket in terms of phase space functions. It carries over to the second quantized theory. Okay, so that's what it is. In particular, if the transformation, the unitary transformation is the dynamical evolution, which is the Hamiltonian transformation, then you can just prove this. Okay, so this is the
Is this document just a set of all?
Yeah. Oh, this is basically it. It's sometimes it's called U infinity. So as you keep so let's say you have a finite level system and you keep increasing the number of things, it's called U infinity. But there are mathematicians have some trouble calling that U infinity because there are other definitions of U infinity perhaps. So exactly. And in fact, this is a well-known fact that unitary transformations become canonical transformations. Okay. So in the classical limit, okay, so this algebra becomes the algebra of Poisson brackets.
Okay. So that Gautam, the set of all functions f such that f star is equal to 1. Where the first star was Moyal star and the second star was 1. That's a unit. And that's a W, right? Because you're imitating that U dagger is equal to 1.
Is
identity.
Yeah, which is what I have called U e to the power little I. Right. Anyway, it's a whole lot of stuff. But using this, you can actually derive. Okay. So these are some plots which have generated for this talk. Okay, I have not derived these things before. You can actually take this little e to the power IA things, and let's say little a is this. So you can actually compute this expectation value in the deformed state. So it's a deformed droplet, and you can actually compute the n equal to infinity. Okay. rigorously by using this, large limit, which, anyway, let me not, I'm already up.
Oh, sorry. How much more time? And there were lots of questions, so if you want to go.
Can I have like 10 minutes? Is that okay? Okay, now here it is. So I go back to the claims that I had made here in this thing. And now I'm going to take the larger limit of this. Okay. So trust me, these things can all be derived. Okay, here it is. So now I take the larger limit in this fashion. So the Moyal bracket has become the Poisson bracket, like this in this equation. U star u has become u square equal to u. Therefore, the solutions of little u are only 0 or 1. Okay. This is some people see these things quite easily. Okay, that of course, this is a Fermi fluid. This has to be droplets and blah blah etc. So this is really the derivation of the droplet. And here is the order 1 phase space density that you mentioned, Sandeep. So that's the normalization. Okay. The first constraint has solutions u equal to 0 or 1. So that's how you get this droplets picture, namely of this kind of stuff. Now so let me make an assumption about phase space droplets, namely that it's a quadratic droplet. What do I mean by that? That at x I draw a vertical, it cuts the boundary only in 2 places. Okay, P minus and P plus. Okay. Then, because of the lack of time, so the uxpt is given in terms of the product of these 2 theta functions, which say that P is between P minus and P plus. Okay. Now you can apply, okay, so first of all, you can identify P plus and P minus with the density, which is the integral of u simply over how many fermions are there, okay, at a particular x. So that's the integral of u over all p, okay, like this. You're counting the number of fermions, so that's P plus minus P minus. Similarly, the momentum density, how much momentum is there in this one, okay, that is given by integral of u with p dp. Okay, so you're counting not just the number of fermions, but each fermion here has some momentum p. Okay, so that gives you p plus square minus p minus square. As a result, the velocity is just given by p plus plus p minus. Okay, so that's your identification. Then you go back to this equation with this thing as a Poisson bracket and apply this one to this theta function formula. So it splits into 2 delta functions. Okay, at each point you have an equation for this, how this p plus of x evolves in time. So that is this. Okay, and similarly p minus of x is the same equation. Okay, coming from this theta function, and you add and subtract to get the same equation as we had got before. Okay, now this has been obtained from first principles. All right. So what's the problem?
Can you explain from the E, which is P plus plus minus y?
Yeah, so the moment total, so you can count the total number of fermions, that gives you the density. You can also count the total momentum. In order to count the total momentum, what you have to do is to, at each point, you don't count only one, which would have been the number, but you say, I have some momentum P here, I have some other momentum P here. You count all the sum over all the P's. That is this integral.
Right.
So that's this one, because the U only says that it's 1 between the upper limit P minus, lower limit P minus and upper limit P plus. So that's what the P plus square is. Then you just do, so the rho V is this, okay, and rho was this. So you divide to get it, okay? All right. So this is what it is. Now you can show that, okay, let me just claim that when this quadratic assumption breaks down, that is to say there's an overhang or a fold that develops, okay, then the del rho del x, precisely at this point, the del rho del x actually becomes infinity. You can just look at the behavior of this P plus and P minus close to this one, and when there are multiple places where this the vertical cuts the boundary, okay, then also you can do this analysis, but rho is not given by P plus minus P minus. Rho is given by P3 minus P2 plus P1 minus whatever there is, and so on. So you look at this boundary and you can show that del rho del x actually becomes infinity. Okay.
Is it that you can work with the classical fluids, so you're working with Poisson brackets, etc.
Yeah.
But in phase space, and therefore that takes care of this.
No. I don't. Yes, that's a very good point. Okay, so let me now say how I deal with this one. This equation is what I'm going to solve. Okay, but this equation is exactly saying that take each fluid particle and evolve it by its own Hamilton equation of motion. Okay, wherever the fluid shape goes after some time t, that's your solution. Okay, that's it. Okay, so this is what we do. So, okay, by the way, so let me say this is a rather generic phenomenon that why do folds form? Why do overhangs form? Because let's say this is one example in which the Hamiltonian is just p squared. Okay, no potential. Then, and this is your xp phase space. Now the top, the fluids in the top region are faster. Okay, so they go like this. So clearly, at this point, there are three routes that have developed. Here, okay, so I have not, drawn this one. Let's say there are two routes here, but here there are three routes that have come. So one route has become three routes because of this overhang. Okay, right? Because here a vertical cuts this boundary only at one place. Here it cuts in three places. And you can immediately show that this del rho del x becomes infinity as well. Anyway, because you know how to evolve this shape, which I have done here, by this exact method, which basically says the following. Maybe I should say that this is what really the solution, integral solution of this one is this. U of xpt at some time t, u of xp is just given by taking u naught and x and if time involving x and b. That's all.
But now u squared is one way, u squared is a normal square.
Yeah.
So u is either 0 or 1.
U is either 0 or 1. As a result, I should evolve only the boundary.
Right.
Absolutely correct.
Right. And this is a remnant of the exclusion principle.
This is a remnant of
so this, in that sense, quantum mechanics has not completely. Because you got this u squared equals 1 from exclusion. Evolution is classical, but
that is correct. That is correct. Quantum mechanics is not exactly gone. So it is only this much of the quantum mechanics. I mean, the Pauli exclusion that. Okay. So now here is the shock treatment. So this is where conventional hydrodynamics stops, and you cannot do it. But we can evolve. Go ahead, and you can see that explicitly. There's a very kinky row that you can keep deriving at every time instant, some kinky row. Okay, this you cannot get as a solution from the conventional, from the conventional hydrodynamics equation. Okay, you just cannot. But we are able to do this.
So Burger's equation will lead you up to the shock, but then beyond it,
you cannot do it. So that is where people tried all these ad hoc terms, but they don't quite work. Okay, so now unfortunately this is related to also something I think Sandeep asked. So this is an example of the free fluid thing in which there is no external potential. Hamiltonian is just p square. So what happens is that again this part is fast, so it reaches here. But I have put periodic boundary condition. So whatever would have gone here, it comes back here. Okay, so you get some filamentation. So you get filamentation. So in the limit of infinite filamentation, this is what happens. Okay, but you can actually prove this. You can actually prove this. I don't have time to do this one, but you can actually use some trick of Poisson resummation and blah 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 etc. to actually show that not only does it reach there, but this density here actually corresponds to the GG density. Okay, I didn't have time to do this, and not only that, you can also show. So this, you can actually do this also for these examples, and there is a never mind. There's a very interesting history of this in which Kedar is also involved.
But that's in the postgrading. Sorry, that previous slide when you looked at the grade, that was because of some postgrading.
This one is a cartoon. Actually, what happens is that it's infinite. It continues to filament more and more and more.
Yeah. So if you postgrade that,
if you postgrade that, you will get that. So in any integral, any kind of, let's say, row of x, okay, or anything like that, or PUP or p square UP and so on, any integral will automatically do that coarse graining, and you will get.
But once the filament becomes type 1 over n, then you should no longer neglect the Poisson, that, and that may actually postgrade.
That might actually, that's a good point. That's a good point. Yeah.
Because the u star u is equal to 1. It's not the same as u square equals 1, then things become type.
Yeah, you have to mean it according to that. Yeah. Good point. Okay, so I have also not only the final stage of this, which is this GGE, but the approach to that is also characterized by these universal exponents. So if you are released from potential x to the power 2m, then there's a power law exponent like that, released from a box potential to a periodic circle, larger circle, then it's like this, and so on and so forth. Okay, there are proofs of these things. Let me just say very quickly our ongoing work. I mean, I have come to it only now, this 517. Everybody, please excuse me. So this is actually also quite beautiful, but I don't have time to get into this. Okay, so here's apparently this is an experimentally realizable situation, which is a rotating Fermi fluid. Okay, so the rotating frame gives rise to these equations, this term, and this is a confining potential. And you have to, your confinement has to be stronger than the rotation of the frame, otherwise the thing will fly off. Okay, so there's an inequality here, and this is actually, so in the limit when this little omega is equal to capital omega, believe it or not, it is exactly the same as the Landau problem. Okay, with these identifications that EB is given in terms of 2m omega, and but even when it is not, even when little omega is different from capital omega, then there is some amount of this non-inertial term that remains. So it's like a Landau electron in a non-inertial term. So and then as it is known to people that in the lowest Landau level problem, these terms do not contribute. So in effect, this introduces constraints in the phase space. There are two constraints in a 4-dimensional phase space, so it becomes a 2-dimensional phase space effectively. So that's what it is. You can do a Dirac bracket analysis. So the Dirac bracket of x and y is non-zero and is given by 1 upon EB. And you can reproduce the spectrum of the system, which is this one. The lowest Landau level usually does not have a spectrum, but by this trick, there's a little bit of, in lowest Landau levels are all supposed to be degenerate. But because I have put a little bit of non-inertial thing, some angular momentum, okay. So, and this effective description actually describes that spectrum very well, and so on. But because it's a harmonic oscillator potential, you see, the effective potential is a harmonic oscillator potential. Harmonic oscillator potentials do not. Okay, so now about dynamics. So this is what happens in a harmonic oscillator potential. You have this, phase space distribution. Harmonic oscillator, what does it do? It says that it's x squared plus, p squared. As a result, all points, all fluid points move exactly at the same velocity. Okay, so no distortion. Okay, so this is what happens after a full cycle of time period. It comes back to itself, just goes like that. However, there is a system which was introduced by these gentlemen, Manas, Satya, and Gregory, which can be explicitly solved, okay, by some Coulomb term like that one. But this one is enough to destroy this uniform angular velocity. As a result, you have these. Okay, if you start from the same initial profile, then you can start seeing these fingers and the filamentation and so on and so forth. So currently we are looking at the equilibration, what it means in terms of equilibration. And here's the conclusion after 521. So we have described quantum quench dynamics studied on two-dimensional fine gas, two dimensions with the limited context, as I said. Large M limit leads to phase space hydrodynamics with a droplet picture, which is exact and does not suffer from spurious singularities of real space hydrodynamics and shock fronts. This allows study of long-time dynamics and approach to equilibrium. We described how universal relaxation rates can be obtained using this method. We are looking at one of our interactions issue, and there's something interesting that you can say also about double scaling. I'm not going to go. And more on the 2D model. In the 2D model, there are lots of questions that, this regular phase space distribution, what does it mean for the real system? Okay, the U of xy is the phase space density of the reduced system. But what has that got to do with the, the real space density, rho of xy, and so on? But anyway, all that for later. Thanks a lot for your patience. I'm done.
Thank you so much for the wonderful talk, Gautam. Let me ask the Zoom audience if there are any questions. Okay, if not, any questions from the audience?
Yeah. When you derive the Euler equation from the U, from the U, you wrote an equation for rho and v, and those two equations only contain rho and v. But it would be not always true that that equation may itself
indeed, that is absolutely correct.
Why it happened that?
So it's not a good point. So a quadratic profile does not remain quadratic for long. So this is what happens. You start with this one, okay, and soon enough it becomes this. So therefore there is no p plus p minus description anymore. There are 4 roots that you can see here. So P1, P2, P3, P4. You start introducing more and more moments. So, so the rho and V, okay, are just two of the variables, which are the two moments of the U phase space distribution. So actual point is that only the phase space distribution, okay, has a closed algebra. Okay, that's a
laptop closed.
Oh, no, I keep something here, I think. Okay, anyway, I'm done.
One quick question.
Hi, Kedar.
Hi. So is there an analog of this where one uses spin coherent states and can look at sort of spin systems that have vortex-like defects and so on?
Okay, I have exactly those slides, and in fact, one little equation, but I cannot show that. So this del T plus H comma U while bracket 0 is exactly the spin coherent thing. Del Tn is equal to n cross B. Okay. And yeah, I can explain that to you. That's the beautiful part. The first time we understood this all was actually in terms of the rotor. So if you wish, all the states of our fermion system are actually can be thought of as W infinity rotors. But the physics is exactly the same as that of spin coherence.
But in spin systems, this quenching is followed by a coarsening dynamics where vortices kind of go away. And now vortices are real singularities, not apparent in the spatial structure. So they can also have a description in this language.
I have to see what you mean, but
I mean, if I take a quantum XY model and quench it from the high temperature phase, or from a quantum quench, then the angular variable which originally has lots of vortices, the vortices have to kind of go away. That's the coarsening process, right?
Yes.
So there's some dynamics that can be formulated in terms of what those singularities are doing and how they are annihilating each other and so forth. And that's usually not so easy to do. It's done in ad hoc ways by writing down some effective dynamics. I wonder if there's a more systematic way of deriving that using something like this.
Yeah, let's discuss this. I'll be very interested.
So my question is group element is done the exponential of the W algebra.
Yes.
So, and the product rule is in terms of this small bracket integration of
yeah.
Wait, sorry, star product.
Yeah. The star product is a little thing. So although these are algebra elements, but these are like matrix algebras, which also have a multiplication. So, like, algebra, if you have a matrix algebra, okay. So Lie algebras are defined in terms of their Lie brackets only. But if you have a matrix representation, they also have a commutation. So this G alpha beta, G alpha prime, beta prime product is in that sense. But when you construct a W infinity group element, you do e to the power I. That's
if n was large but finite, then this description seems to change a lot. Because now you no longer keep track of a surface, you keep track of the whole function, and also evolution becomes non-local. Right, because the star product is non-local.
Yeah.
Is there anything to say about that evolution?
So we have only looked at the first order. Okay.
So that will be a subpopulation.
Yeah.
But suppose n was finite. Anything?
Yeah, I'm not sure. I mean, it's hard to beat the actual quantum mechanical calculation in that case.
Probably just a little bit.
Yeah. So with Ajay, we have looked at the first order deformation of this Moyle bracket thing.
Any further questions? If not, let's thank Dr.